Thanks for joining me for subsection 6.4.3 on the determinants of special matrices. Example 6.4.6. Evaluate this determinant. We saw in the previous video that the most efficient choice is going to be the row or column with the most zeros. Well, this one has the most zeros. In fact, they're all 0. So if we do our grid plus minus plus minus plus, then our determinant is equal to, well, it's plus 0 minus 0 plus 0, and I've left off the minors because it doesn't matter because they will be multiplied by 0 anyway, and so I get a big fat goose egg, right? So the takeaway, this obviously, anytime you've got a row or column of zeros, you can always imagine expanding along it. So the determinant of a matrix that has a row or column of zeros is equal to 0. Example 6.4.7, evaluate this determinant. Now there's a lot of zeros here too, but there's no full row or column with all zeros. So I'm still going to choose the row or column with the most, and that's going to be this one, right? So I'm going to do column 1 there. There's also row 5, which could work just as well, but I'm going to choose to go down column 1. So plus, minus, plus, minus, plus, and so this determinant is equal to 2 times plus 2 times the minor, and I remove that row and column. So I have this determinant now, which is a 4 by 4. So minus 378 minus 3211, 0, 1, etc. here, minus 91 and 0, 0, 6, 18, 0, 0, 0, 2. Right, and then minus 0 plus 0 minus 0 plus 0 for the rest of the entries down the columns. Now, this is a 4 by 4, so I have to do cofactor expansion. Again, we'll look at the shape of it. The shape of it, I've got zeros in that lower portion of the matrix, just like I did up above. So I'm going to do the same old trick. I'm going to go down column 1 again. So that means I've got the same grid. Now this, right, this is not the entry that's here. I mean, it is, but it is in a new matrix. It's now in the top left corner. So it starts again as a new plus, plus, minus, plus, minus. Now I'm going to stop writing these plus zeros and minus zeros because we know they give us nothing. So I'm going to end up with my original entry 2 times, open a bracket, minus 3 times, and then remove the row and column that minus 3 is in. So I get the determinant of 165 minus 91, 0, 6, 18, 0, 0, 2. Now this is a 3 by 3, so in theory we could do Sarris's rule, but I am on a roll here. I have the same pattern again. It's getting smaller and smaller and smaller, so I am going to go right down that first column again with cofactor expansion. So plus, minus, plus. Again, these now are irrelevant to me because I know that just as I did in the first, I'm going to end up by multiplying by 0, so I'm not even going to bother writing them. So this is 2 times minus 3 times. Now I'm doing this minor here, so 1 as the entry. 1 times. You'll notice that I didn't multiply these together to give minus 6. I could have, but I'm developing something. I'm going to show you that is a lovely pattern developing. So if you're wondering why I'm not simplifying, then just hold on for a second. There's a good reason. So 1 is my entry, which means now I'm deleting the row and column that that 1 is in. So then I have the minor of 6, 18, 0, 2. And this is a 2 by 2 matrix. This is a 2 by 2, so I can do AD minus BC, which is what I am going to do. Now, this, again, I'm not going to multiply. So 2 times minus 3 times 1, and this is 6 times 2, which I would normally just write as 12, minus 0, right? 0 times 18. So 2 times minus 3 times 1 times 6 times 2. Do we notice that? Before I even evaluate this, all right, well, I'll just evaluate it minus 72. But look at what this is. Look at what this is. 2 times minus 3 times 1 times 6 times 2. Where are those numbers in the original matrix? 2 times minus 3 times 1 times 6 times 2. They are there. They are the numbers along the main diagonal. And that will always be the case because whenever we have a matrix of this form, right, this is an upper triangular form, we can always imagine expanding down the first column every time and having this pattern develop. And so that is the takeaway here, the determinant of an upper triangular. Now this could also happen if we had a lower triangular, because then we would just evaluate along a first row instead of a first column, triangular, or even a diagonal matrix. A diagonal matrix, which is actually both lower and upper triangular. It ends up by being just the product of the entries on the main diagonal. And so that is information that we can use in example 6.4.8. We're asked to evaluate A, the determinant of this matrix. Well, this matrix is lower triangular, right? This is a lower triangular matrix. And so I can imagine, I can actually do the expansion. Yes, I could do Sarris's rule or do the expansion every time. But if I imagine going along row 1, then I have exactly the same thing that happened in the previous example. A first entry with a bunch of zeros. So this lower triangle is going to act exactly like the upper triangle did in that the determinant is going to be the product of the entries along that main diagonal. So let me write this down. 2 minus 3, no, 2, 0, and 0 for minus 3. That is going to be 1 times 0 times minus 3, or just 0. I. What is I but a diagonal matrix? Right, so I, it doesn't matter what size. Notice I don't write IN or any size, right? I is a diagonal matrix that has ones everywhere on the diagonal and zeros elsewhere, right? So this is a diagonal matrix, and so the determinant of I for any size, right? This is for any n, this is IN for any n, is just, well, the product of that diagonal. So determinant of I is 1 times 1 times 1 times 1 times 1, or just 1.